In the world of option pricing, the binomial model is a powerful and intuitive tool that helps us understand how an option's value evolves over time. However, the standard model operates in a simplified world, one where companies never return cash to their shareholders. In reality, many companies pay dividends, and this seemingly small detail can have a significant impact on the option's price. Today, we are going to explore exactly how to adjust the classic binomial option pricing model to correctly handle stocks that pay dividends. We look at two primary types of dividends and implement both solutions step by step in code. This is a critical skill for anyone looking to build a robust and accurate pricing engine. So, why is a simple dividend payment such a big deal for our models? The standard binomial model assumes that a stock's price follows a random path, moving up or down by certain multiplicative factors at each step in a pricing tree. But a dividend payment is different. When a company pays a dividend, it is distributing a portion of its corporate value, its cash, directly to its shareholders. Consequently, on the day the stock goes ex dividend, its price mechanically drops by an amount roughly equal to that dividend. This is not a random market fluctuation, it is a predictable scheduled event. A standard model, which only accounts for random up and down movements, will be fundamentally incorrect if it ignores this known leakage of value from the stock price. A lower expected future price has a direct and predictable impact on option values. Call options, which give the right to buy, becomes less valuable. They have a lower chance of finishing in the money, so the price should be cheaper. Put options, which give the right to sell, become more valuable. They have a higher chance of finishing in the money, so the price should be more expensive. To be accurate, we absolutely must adjust a model to account for these payouts. In the world of quantitative finance, we model dividends in two primary ways, each requiring a different solution. First, we have the continuous dividend yield, usually denoted by Q. Imagine the stock is a leaky faucet, constantly dropping out a small, predictable percentage of its value as cash. This model is not very realistic for a single stock, but it's an excellent approximation for a broad stock market index, like the S&P 500, where hundreds of companies are all paying small dividends at different, seemingly random times throughout the year. The solution here is elegant. We adjust our risk-neutral pricing framework. Normally, we assume a stock grows at the risk-free rate R in the risk-neutral world. With this continuous leakage, we simply assume it grows at a lower rate R minus Q. It's a simple tweak to our core assumption. The second and more common for individual stocks is the discrete cash dividend. This is when a company announces it will pay a specific cash amount, say, for example, like $2.50 on a specific future date. This is a known certain cash flow. The solution here is quite clever. We conceptually split the stock price into two components, a risk-free component, which is the present value of the promised future dividend, and the risky component, which is everything else. We then perform a binomial model only on the risky components. It's like modeling the value of the company's core business operations, separate from the cash it's about to hand out. Let's bring this to life with some code. We're going to build a multi-step binomial pricer to see exactly how a continuous yield affects an options price. Here, our parameters are stock at $100, a strike at $100, 1 year to maturity, 5% risk-free rate, and a 20% volatility. We'll compare a no dividend scenario to one with 3% continuous yield. The core of the code is a standard binomial pricer, but with one critical adjustment here. When we calculate the risk neutral probability P, instead of using the risk free rate R, we use R minus Q. This small change incorporates the dividend yield into the entire tree. We send the parameters we discussed earlier into this binomial pricer function. For a call with no dividend or a put with no dividend, we simply plug in the value of Q as 0. And for with dividends, we plug in the value of Q. So let's run this code. Look at the results. For a call option, the price with no dividend is $10.4306. And with 3% yield, it drops to $8.633. For the put option, the price with dividend is $5.55. And with the 3% dividend yield, it increases to $6.7117. This is exactly what the theory predicted. The leakage of value from the dividend hurts the call and helps the put. Now, for the more common case of a known cash dividend, our problem is this: a stock is at $100. In 6 months, it will pay a 2.50 dividend. We want to price a 1 year option on this stock. The logic here is different, and it's a multi step process. Step 1, we calculate the present value of the future dividend of the stock and subtract it from today's stock price. we are effectively removing the risk-free part of the stock's value. We build the entire binomial tree using this new adjusted starting price. This tree now models the random movements of only the risky part of the company's value. So the step 2 is to build the tree using the adjusted stock price. So we have already done a more detailed construction video of the binomial option pricing tree. So the step 2 is to build the tree using the adjusted stock price. At maturity, we calculate the options payoff. Critically, we use the actual stock price, which is the price from an adjusted tree. We don't need to add the dividend back because at maturity, the dividend has already been paid and is no longer part of the stock's price. So most of the parameters are same with two new parameters for this function, which is the dividend cash and the dividend time. So just like the previous snippet, for pricing with no dividend, we just put the dividends cash as 0 and we do not plug in the dividend time value. Let's run this code snippet. And the results again come from a theory. The call option price drops from 10.4306 to 8.9699, and the put option price increases from 5.5536 to 6.5311. The effect is similar to the continuous yield, but calculated in a more precise, event-driven way. So, as we have demonstrated, pricing options on a dividend-paying stock requires a crucial adjustment to our standard models. Dividends represent a known non-random leakage of value from a company, and the pricing must reflect that. For continuous dividends, like those on broad market indices, the solution is to adjust the expected growth rate in our risk-neutral probability calculation from R to R minus Q. For discrete cash dividends, the standard industry practice is to subtract the present value of all future dividends from the current stock price and build the binomial tree on this adjusted purely risky component of the future stock's value. Failing to account for dividends is a common mistake that will systematically overprice your call options and underprice your put option. Properly handling them is a critical step in moving from a basic academic model to a robust and accurate real world pricing engine.